Hello and welcome to the 22nd lecture of analog integrated circuit design. In the previous lecture, we discussed the large signal model of the MOS transistor as it appears on an integrated circuit in some detail. We saw that it obeys square law when the VDS is greater than a certain amount. We also saw that the bulk voltage has a significant influence on the current in the MOS transistor. This is because the bulk and the gate are similar in a MOS transistor, they play similar rules. In an NMOS transistor, increasing the gate voltage or the bulk voltage increases the amount of charge in the channel and leads to an increase in the current. Okay. Modeling the effect of the bulk is quite important in a MOS transistor, especially on an integrated circuit. We also saw that we also discussed the behavior of the MOS transistor when the VGS is below the threshold voltage, and we saw that it turns out to be an exponential. Okay. Now, as I also mentioned in the last class, the real model of a MOS transistor is very complicated. So, you have to use a simulator to gain a better understanding of the MOS transistor. So, what I suggest that you do is take it as an exercise to get hold of some MOS transistor models. In fact, some models are available from this website. Okay. A number of models are available. You can choose the 0.18 micron CMOS process models. Okay. And you take these models, get familiar with the circuit simulator. There is a number of circuit simulators available, both free and commercial simulators. You can download some of the free ones off the web, and the kind of exercise that I am going to mention can be very well done on a free simulator. Okay. So, please do the following. Plot ID versus VGS of NMOS and PMOS transistors. When I say VGS for a PMOS transistor, it means the VSG, of course, okay, in saturation region. And similarly, plot ID versus VDS of NMOS and PMOS transistors. For a range of VGS values, okay, that is with VGS as a parameter. Now, we will have to do this kind of exercises anyway when you come across the process for the first time. Now, this also helps you understand the limitations of the model that we have. Okay. The model that you have on this website are quite complicated, they model the MOS transistor very elaborately. So, when you do these two things, let us say you choose the 0.18 micron CMOS process. As I mentioned earlier, when you specify a length of a process, it means usually the minimum gate length that is possible for a MOS transistor. Okay. You try these for different values of W by L. Okay. So, let us say I will say 1.8 micron by 0.18 micron. Okay. You can double both of them. Similarly, double it further. Okay, let us say you take these 4 values, you could also take other things in between. The point of these values is that all of them have a W by L ratio of 10. but as I mentioned earlier, there are lots of effects which make the transistor's characteristics deviate from square law. Now, one thing that we did not discuss is the short channel effect. When the channel length becomes very small, then it is definitely not a square law device. Okay. It turns out that when the channel length is very short, okay, it is not a square law device. Now, again we have not discussed the device physics, but the square law comes from two different dependencies on Vgs minus Vt. First of all, the amount of charge depends on Vgs minus Vt, and the electric field inside the device depends on Vgs minus Vt, and in a certain region the velocity of the carriers is directly proportional to the electric field. So, the total current is related to the number of carriers, which is related to the total amount of charge times the velocity of the charges. Since each of these is dependent on Vgs minus Vt, we get Vgs minus Vt squared. Now, it turns out that as you increase the electric field beyond some limit, the velocity of the carriers becomes saturated. Okay, this is known as velocity saturation. So, at this point the velocity of the carriers no longer increases with the applied electric field. So, this means that now the total current equals the product of speed, which is more or less a constant, times the amount of charge, which is proportional to Vgs minus Vt. Okay. So, the current, instead of being instead of that, what you end up getting is okay. It turns out that this is the speed of the carrier. Okay. So, the velocity saturated current is given by something proportional to Vgs minus Vt and the saturation velocity of the carriers. Okay. Now, because of these reasons, the transistor current does not obey an exact square law dependence with Vgs. Okay. And also another thing to keep in mind is that the regions are not abruptly divided into, oh, here we have velocity saturation and here we do not. Okay. Like all physical phenomena, these happen continuously. So, the bottom line is that if you do the characterization for these sets of channel lengths and channel widths, let us say 1.8 micron by 0.18 micron all the way to 14.4 microns by 1.44 microns, all of them have a W by L ratio of 10, but you will see that the behavior will be quite different. Okay. In fact, in particular you should try to identify these things, the regions in which square law is indeed obeyed and the region in which the square law is not obeyed. Okay. And these things can be found from the plot of ID versus Vgs in the saturation region. Okay. And also by plotting either ID versus Vgs or square root of ID versus Vgs, you will also be able to identify this threshold voltage, which is what we use in our simple model. Okay. And the ID versus VDS will give you the value of lambda and other things, how the transistor current depends on VDS in the saturation region, how it depends on that in the triode region and so on. Now, finally, if you observe properly, you should see that as you increase the channel lengths to very large values, it will obey square law. Okay. And as you reduce the values of channel length, it will not obey square law, but you should still be able to design circuits with these transistors whether the current obeys square law or not. Okay. So, this is one of the exercises, and the other exercise is to find out the current in subthreshold region. Okay. For this, what you do is plot ID versus VGS on a log scale. As you know, the log scale is used when the quantities cover a wide range, and as I said, when VGS goes below the threshold voltage, the currents will be so small that they can be meaningfully represented only on a log scale. Okay. You can plot ID versus VGS and you cover a range of VGS which includes values less than Vt. Okay. Now, I already said that ID will be proportional to exponential VGS divided by the thermal voltage times some factor eta. Okay. Now, if you recall, a perfect bipolar transistor will have eta equal to 1, a MOS transistor will not have eta equal to 1. In fact, all of these things you can estimate from this plot. When it is following an exponential, the curve ID versus VGS, where ID is on a log scale, will be a straight line. Okay. And this will be the subthreshold region, or the weak inversion region, and when you go above the threshold region, it is square law, which means it is less steep compared to an exponential, and it does something like that. Okay. So, the point of this exercise is first of all to identify the subthreshold region, and secondly, from this region you can get the slope eta. Okay. You can calculate what the slope should be and what the slope is of this straight line, and from that find the factor eta. Okay. We will discuss this a little more later, but you can see that if eta is close to 1, then it will be better because the exponential will be really steep. Okay. So, that is the point of this exercise. Again, do this for both NMOS and PMOS and familiarize yourself with the MOS transistor. Now, finally, the third exercise would be to find the effect of VSB. Okay. You take a MOS transistor and bias it with a fixed VGS and VDS, and you vary VSB. Okay. And let us assume VSB is more than 0, so that you do not forward bias the source bulk junction, right. And now you can plot ID versus VSB. Let us assume that you have maintained VDS and VGS, so that it is in strong inversion and saturation. Okay. So, this is one of the exercises, and secondly, you can also plot ID versus VDS for different values of VSB, okay, with VSB as a parameter. Remember, earlier you plotted ID versus VDS with VGS as a parameter. For different values of VGS, you would get different saturation currents. Now, if you do the exercise correctly, you will see the same effect with VSB as well. Okay. This is again to convince yourselves that the back gate and the front gate have qualitatively similar functions. Quantitatively, of course, they will be different from each other. Okay. So, the previous lecture plus all these exercises should give you a very good idea, very good handle on the large signal characteristics of the MOS transistor. Okay. So, we will now move on to small signal model of the MOS transistor. Okay. Because ID is a function of VGS, VDS and of course VSB, or in the small signal case it is usually written as a function of EBS. We know that the change in ID will be a function of change in VGS, change in VDS and also change in VBS. And what kind of a function will it be? We know that when these changes are small, it will be a linear function. Okay. So, delta ID will be partial derivative of ID with respect to VGS at the operating point times delta VGS plus partial derivative with respect to VDS again at the operating point, which is very important, times delta VDS plus partial derivative with respect to VBS times delta VBS. Okay. Now, it is common to denote changes by lowercase letters, which is what I am going to do here onwards. This is VGS, VDS and VBS, and this could be represented instead of delta ID as lowercase ID. Okay. And this behavior is what is captured by the small signal model of the MOS transistor. Okay. So, first of all, to represent the dependence of ID on VGS, we need to have a control source. This is a linear control source, like everything in the small signal model is linear, and the value of the control source is dou ID by dou VGS. Okay. So, we have 4 terminals: drain, gate, bulk and source. So, between the drain and source, we will have a controlled current source, and this denotes this particular current, and this constant, as you are probably aware, is called GM. Okay. So, this current is GM times VGS, where VGS is the small signal gate source voltage. Similarly, this current can be represented by another control source, and this constant here dou ID by dou VBS is like GM, but from the bulk. So, it is usually denoted by GMB. Okay. And in the small signal case, we use VBS instead of VSB, that is the convention, and this control source is GMB times VBS. And finally, this current here, it relates the current from drain to source as a function of voltage between drain and source. We could use a controlled current source, but it is easier to just model it as a conductance, okay, because the controlling terminals on the where the current is flowing are the same, and this quantity is known as GDS. Okay. So, this is a conductance which is GDS, right. Now, this is the DC small signal model of the MOS transistor. The leftmost source, it denotes the current from drain to source based on the increment in VGS. The conductance GDS denotes the dependence on drain to source current on the drain to source voltage in the small signal sense, and finally, GMB times VBS denotes the dependence on drain current on the bulk source voltage. Okay. And because this does not include any capacitors or charge storage effect, this is the DC small signal model of the MOS transistor. Okay. So, this is what we will use for DC small signal analysis. Here onwards, I will simply write GM here. It is understood that it multiplies VGS, and I will write GMB, and it is assumed that it multiplies VBS, and I will write GDS here. This is just to simplify the diagram and reduce clutter. Okay. Now, this is the DC small signal model. Now, in addition to this, let us take again an NMOS transistor. Now, first of all, there will be a capacitance between the gate and channel, because after all that is what a MOS transistor is. It is a capacitance that is formed between the gate and the inversion layer when the transistor is on. Okay. So, this contributes to some capacitances in the circuit. Now, this is really a distributed capacitance. The capacitance goes between the gate, which stretches all the way from here to there, and the inversion layer, which also stretches all the way from here to there. Now, we have to represent it as capacitor between discrete terminals, drain, gate and source. So, what we will do is, we will apportion the capacitance into two parts, one between the drain and gate and one between gate and source. Okay. This is called CGD and this is called CGS. Okay. Due to the depletion region, there will be a capacitance between drain and bulk, which is CDB, and between source and bulk, which is CSB. Okay. It is primarily due to the depletion region below this diffusion regions. Okay. Now, these are the CGD and CGS are intrinsic to the operation of the MOSFET. As we know, MOSFET is nothing but a capacitor. Okay. The capacitor controls the charge in the inversion layer and in turn controls the current. So, these capacitors will always be present whenever you have a MOSFET. Without this capacitor, there is no MOSFET. Okay. Because the CGD and CGS, the what we described so far, come from the intrinsic capacitance between the gate and the inversion region. So, these are known as intrinsic capacitances. Okay. And the value of these things depend on the operating point. Okay. Now, it turns out that in triode region, CGD and CGS are both equal to half of W times L times Cox. Okay. This W times L is nothing but the area of the gate and Cox is the capacitance per unit area of the oxide under the gate. W times L times Cox is the total capacitance of the gate. Now, in triode region, these are equally apportioned between the drain and the source, both CGD and CGS equal half WL Cox. Okay. Now, this you can easily imagine. Again, you imagine a case where the drain and source voltages are identical, then the channel will be perfectly symmetrical, and then clearly the configuration between the gate and drain will be the same as that between gate and source. So, the proportion of charges allocated to drain and source are identical. As you go away from deep triode region, the charge distribution becomes less and less symmetrical. Okay. And we will have a different charge distribution, and in the extreme case in saturation region, CGD will be 0 and CGS will be 2/3 WL Cox. Okay. This all these come from device physics by calculating the amount of charge in the inversion layer. Okay. The total charge is 2/3 WL Cox and all of it is apportioned to the source. Now, nothing is apportioned to the drain because at the drain end the channel is not inverted and there is pinch off. So, nothing is really connected to the drain, so to speak. Okay. So, these are the values of CGD and CGS. By the way, this model is valid in all regions, okay, including GM, GMBS and GDS. The only question is what the values of those things are. Now, we will be using this model mostly in the saturation region because that is where we operate our amplifiers, but the model itself is valid everywhere. Okay. Now, this is about the intrinsic capacitors. In addition to this, you see that you have some conducting material here. In addition to this, you could also have these wires and you have the conducting gate, and between these two there will be a capacitance. This is not inherent to the operation of the MOSFET, but it is there simply because there are two pieces of conducting material are close to each other. Okay. So, the actual CGD and CGS will consist of this plus some overlap capacitance and that plus some overlap capacitance. Okay. Now, again drawing the picture of the MOSFET. If you want to calculate the overlap capacitance between these two, you imagine the top view where the gate is like that, okay, and the drain and source regions are like that. Okay. Now, this capacitance is nothing but the fringing capacitance between this conductor, which is the gate, and this is which is the drain. Okay. And you can easily see that the capacitance will be proportional to the width of overlap, which is nothing but the width of the MOSFET. Okay. It is something proportional to the width, and it the same thing is true for CSB as well. Okay. So, I will denote these as COV prime, which is the capacitance per unit width times the width of the MOSFET, and exactly the same thing holds for CGS as well. This is plus COV prime times W. Okay. So, those are extrinsic capacitors, but they will be there anyway when you have a MOSFET. So, you also have to model them. Now, regarding CSB and CDB, now CSB is basically the junction capacitance of the source junction, okay, this one, and CDB is the junction capacitance of that junction. Now, exactly how much the capacitance is depends on the area of this face, okay, the bottom face of this and also the side faces of. Now, again if you look at the top view of the MOS transistor, this diffusion region N plus will have some length, let me call that LD, and this is usually of the same length LD. Okay. And typically as a guideline, if you do not have any other information, you can assume that LD is 2 times the minimum length of the gate in a given technology. Okay. And this dimension is nothing but W. And as usual, we do not have control over this depth. That is why we do not want any parameters describing the depth. If we know the depth times W is the sidewall area, okay, but we do not want any of that, the depth is fixed. So, the capacitance is described as being made up of 2 pieces, one which is the overlap area at the bottom, which depends on W times LD. Okay. So, each of these things consists of what are usually called the area capacitance, which refers to the overlap area at the bottom plus some perimeter capacitance. As I described while defining the sheet resistance and so on, in an integrated circuit we have control over only the 2 dimensions. So, all the other dimensions are abstracted into parameters, and we will describe everything into dimensions that we can control, which is LD and W and so on. Okay. Now, the area capacitance part is given by W times LD, which is usually called AS, the area of the source, times some capacitance per unit area plus the perimeter of this, which is 2 times W plus LD times C perimeter. Okay. And this parameter is usually denoted PS while you describe the MOSFET in a simulator. Okay. Now, we are of course looking at regular structures which have a rectangular area, but you could also have other odd shapes. So, then you specify the area and the perimeter directly of the source and drain junctions. Similarly, for the CDB we will have AD, that is the drain junction area times the capacitance per unit area plus the drain junction perimeter times the capacitance per unit perimeter. Okay. Now, these are all details, but you need to know these things when you want to describe these things in a simulator. Okay. When you model a MOSFET in a simulator, you also have to put in appropriate perimeter and area values for the MOSFET, so that you model all these capacitances. We will later see that all these capacitances will have significant influence on the operation of the circuit. So, it is very important to understand these models and then use them properly. Okay. So, just to summarize, the small signal model of the MOS transistor consists of DC parameters, which are GM, GDS and GMB, and capacitances, which are CGD, CGS, CSB and CDB. Okay. Between every pair of terminals you have a capacitance, except between source and drain directly, because they are kind of isolated from each other, and that capacitance is generally small in most processes. Okay. And in saturation region, the intrinsic value of CGD is 0, but you will have the overlap capacitance per unit length times the width of the MOSFET. CGS will be 2/3 Cox WL plus this times the width of the MOSFET. CSB and CDB are junction capacitances and largely independent of the region of operation of the MOS transistor. We will of course assume that these junctions are reverse biased, otherwise these capacitances will be very different, and it is the area of the source junction times the source junction capacitance. Maybe to explicitly mention that, I will say Cj area plus the perimeter of the source junction times Cj perimeter, and this will be area of the drain junction times Cj area. Because the junctions are of the same type, the same Cj area applies to both CSB and CDB. Okay, plus PD times Cj perimeter. Okay. And GM, GDS and GMB can be calculated in the saturation region. We can also calculate it in the triode region, but because saturation region is of greater interest, that is what we will use. Okay. So, again we will start from the square law, which basically assumes a strongly inverted MOSFET operating with VDS greater than VGS minus VT, and I will do my calculations with an NMOS transistor, but they can be easily translated to a PMOS transistor. This is the expression for the current, and the transconductance GM is given by dou ID by dou VGS, which is equal to mu on Cox W by L VGS minus VT 1 plus lambda VDS. Okay. Now, first of all, this lambda VDS is expected to be a relatively small quantity compared to 1. Now, this is largely true except when the channel length is very short. Now, for simplicity of hand calculations, many times this is simply approximated into mu on Cox W by L VGS minus VT. Okay. Now, if you look at this, this can also be written as 2 times the drain current divided by VGS minus VT, and also you can neglect this 1 plus lambda VDS and write it in terms of only ID. Okay, 2 mu on Cox W by L times ID. Okay. So, these are all just rearrangements of the same expression, and in here and here we have omitted the 1 plus lambda VDS, that is we have replaced 1 plus lambda VDS by just 1 for simplicity, and this is the kind of thing that you have to do for hand calculations. There is no point including all kinds of small details when the model itself is inaccurate. When you want really accurate answers, you go to a simulator, but it is very important to do hand calculations, because you know which way the circuit has to be modified when it does not give you the result that you want. Okay. Now, these 3 expressions appear to show different dependencies of GM over the electrical quantities VGS minus VT and ID. Okay. Now, the first one says it is proportional to VGS minus VT, but the second one says it is inversely proportional, but there is no contradiction here. This is a function of only VGS minus VT, but this is a function of ID and VGS minus VT. If you change VGS minus VT for a given transistor, ID will also change. Okay. So, you have to take that into account, so do not get confused by this. And finally, the last one says it is proportional to square root of ID, but this is expressed only in terms of ID. Okay. So, each of these we will use in the right context, because many times you change one parameter and you would like to find the influence of only that parameter. So, let us say you change only VGS, then the first expression is most convenient, and let us say you make some manipulation by which you change only the drain current, then the last one is most convenient, and the second one is also quite convenient sometimes when you want to get some insight into the operation of the circuit. Okay. Now, it is the second one that I want to discuss in a little more detail. It says that GM is 2 ID by VGS minus VT. Now, this seems to suggest that if I go on reducing VGS minus VT while maintaining a constant current, and how can I do this? I can go on increasing the width of the transistor and reducing VGS minus VT. We know that ID is proportional to W by L and also proportional to VGS minus VT square. So, I can reduce VGS minus VT and increase W by L and keep current the same, and this thing says that as VGS minus VT approaches 0, GM approaches infinity. Okay. So, do you really think that will be the case? Now, what really happens is that the square law model is valid only when VGS minus VT is greater than about 6 VT, where this is the thermal voltage. Okay. Now, when VGS approaches very close to VT, then the square law model itself is invalid. It is valid when VGS minus VT is more than about 6 VT or approximately 150 millivolts. Okay. Now, for VGS minus VT values below this, you can't use the square law model. So, this expression which is derived from the square law model is also invalid. Now, what happens in the subthreshold region? ID is given by some I naught exponential VGS divided by eta times the thermal voltage, where eta is some parameter, and you have to calculate the GM from this expression, and if you do that, you will see that it will be ID divided by eta VT. Okay. Now, these expressions are in a similar form. The first one can be thought of as ID divided by half of VGS minus VT, and the second one is ID divided by eta VT. So, what happens is you imagine a case where the transistor is biased with a large VGS minus VT, then you go on increasing the W by L and go on reducing VGS minus VT, okay, while maintaining the current to be constant. This is possible with some combination of decreasing VGS minus VT and increasing W by L. Now, what happens is as W by L increases to very large values, VGS minus VT reduces and the GM value will saturate, it will not go on indefinitely increasing. Okay. This happens when the transistor enters subthreshold region. Okay. So, this is an example of where you can calculate an expression based on some model, and then it seems to give you absurd result, but it turns out that the model itself is invalid. Now, the other thing this says is that for a given current, where would you operate, in which region would you operate to get the maximum GM? Later we will see that getting a large GM is a very important thing in electronic circuits. Okay. Your GM is something like the gain of the transistor. Okay. So, getting a large GM is quite important, and you easily see from these expressions that if you want a large GM, you should operate with as small a VGS minus VT as possible, and in fact push the transistor into the subthreshold region. You use a very large transistor and bias it with a relatively small current, then you get the largest value of GM divided by ID, that is you get the most bang for the buck, meaning you get the value of GM with the smallest amount of current, or for a given current you get the largest possible GM. Okay. And these are all things that we will use later when scaling circuits, etc., but again something to be kept in mind, because this is how the small signal parameters behave. So, in this I will write one particular form of this, which is 2 ID by VGS minus VT. This is in strong inversion, or ID divided by eta Vt, where this Vt is different, it is the thermal voltage and this is in weak inversion. Okay. Now, GDS, which is dou ID by dou VDS, is given by mu Cox by 2 W by L VGS minus VT square times lambda, and as before this itself is approximated by the current and we will make this lambda ID. Okay. So, a good approximation for the value of GDS is lambda times ID. And finally, GMB is dou ID by dou VBS. Now, VBS is not explicitly apparent in the expression, but we know that Vt is a function of VBS. Okay. So, what we have is, let me use chain rule, dou ID by dou Vt times dou Vt by dou VBS, which gives me minus mu Cox W by L VGS minus Vt 1 plus lambda VDS times dou Vt by dou VBS. Okay. Now, because VSB equals minus VBS, I can write this as dou Vt by dou VSB and make this a plus sign. Okay. And you also see that this part of the expression is nothing but the GM of the transistor, it is GM times dou Vt by dou VSB. Okay. So, it is something proportional to GM, and this dou Vt by dou VSB is a number that could be of the order of let us say half to 1/4 or maybe slightly smaller. It is not a very small number, nor is it more than 1, it is typically less than 1, but maybe between half and 1/4 or something like that. Okay. So, this GMB, the transconductance from the back gate or the bulk, can be a significant fraction of GM. In some cases this is actually used for useful functions in circuit design, but usually the constraint that you have to reverse bias the source bulk junction limits the utility of this GMB, okay, although it can be used in many cases. And in some cases it is a hindrance, we will later see some basic circuits where this leads to some problems. Okay. So, this completes the small signal model, and later when we realize transconductors and op amps and so on with our MOS transistors, we will use the small signal model to evaluate the characteristics of those blocks. Okay. So far we have discussed the common components like resistor and capacitor, and we have also discussed the MOS transistor. Now, in case of resistor and capacitor, we saw that when you make physically identical components, they are nominally identical, there will be a small mismatch between them, and that is related to the physical size of the device. Exactly the same thing is true in case of the MOS transistor as well. We will now quickly deal with mismatch in MOS transistors. So, let us say you make two identical MOS transistors. I will show the top view. They have some W and some L, and there is a copy of this which has the same W and same L. Okay. So, these two are nominally identical, that means that if you bias it with a given VGS, VDS and VSB, you should get the same current. Okay. Now, as usual it turns out that things are not exactly identical, they are only nominally so. there is a small difference between the two. Now, how do you describe the difference between these two? In case of resistor and capacitor, we have a single parameter, right. We have the resistance of the resistor, we have the capacitance of the capacitor, whereas in case of MOSFET we seem to have many parameters. But first of all, we will use the square law model in saturation region, which says that it is mu Cox by 2 W by L Vgs minus Vt squared, and this entire multiplying factor, let me call it beta by 2 Vgs minus Vt square. Beta is nothing but mu Cox times W by L. So, now there are really only two parameters, beta and Vt. Okay. So, we will describe the mismatch in beta and Vt. That is, what we do is, let us say we make 10,000 pairs of these transistors and measure the difference in beta and measure the difference in Vt for each pair of transistors, and somehow describe it and also relate it to the nominal value of beta and Vt. Okay. So, the Vt mismatch is described by the standard deviation of Vt, and in case of Vt it is not normalized to the nominal value of Vt. Okay. This is because the nominal value of Vt could be 0 or very small. Okay. So, it does not make any sense to normalize it to the nominal value of Vt. We will see that Vt is nothing but just the sigma of Vt1 minus Vt2 for each pair of transistors. Okay. And this is a quantity that has dimensions of millivolts, unlike the mismatch in resistors and capacitors, which were relative mismatch and were dimensionless. Okay. And this is given by some constant that depends on the process divided by the area of the MOS transistor, exactly the same way that resistor and capacitor mismatch depended on the area. And beta mismatch or the current factor mismatch, this it has some nominal value and it is multiplying this. So, this is really the sigma of beta 1 minus beta 2, that is the difference in betas of nominally identical pair of transistors divided by the nominal value beta naught, and this is given by A beta by square root of WL. Sigma Vt is something that is measured in millivolts and sigma beta is something that is measured in percent. Okay. Sigma beta is analogous to the numbers sigma r and sigma c. Okay. So, how do we calculate the effect of these mismatches? We will see that in the next lecture. Okay. Thank you.